We're going to look at an equivalent resistance problem, but it's a little bit more than that. We're going to get hopefully a better sense for the junction law and loop law, Kirchhoff's law, as, and we're going to do so with this problem, which really kind of annoyingly asks us for what are the currents and voltages across every element in the circuit. And so that would be the three resistors, R1, R2, and R3, and the battery. You see the little omega symbol, the Greek letter omega symbolizes ohms, and so we can tell that these are resistors, even if we weren't told. And R, just in general, is the unit of resistance, which has units of ohms. And the resistance tells you, I guess, how much the current will be slowed down and how much we're going to fight the current as the current tries to make its way through this circuit, which actually contains both parallel and series components. I would really recommend that you watch the one where we combined capacitors. I'm going to sort of gloss over those combinations this time around, not focus on them, and instead focus on sort of understanding the answer and understanding how are we going to introduce Kirchhoff's laws into this problem. So what we do find in terms of combining resistors, we're going to combine these resistors into effective resistances. And so this first one is going to look something like this, right? Both of them actually are going to look the same. We want to sort of transform circuits into pieces where there's only one sort of equivalent or effective resistance against that same battery. The rules are very similar to the capacitor, so I'm not going to go into strict detail on that end, except the difference is that the opposite applies as to series versus parallel. Whereas in capacitors, two capacitors in parallel add up in the normal R1 equals R2 plus R3 way, or I guess for capacitor C equivalent equals C1 plus C2. For resistors, in series, they're going to add that way. And that's because for a resistor, if you have to go through one, if you're a piece of charge trying to get through one, and then you would have to get through the other, you would get blocked by both resistors. And so it's like having a twice as effective resistance when you have a resistor or two resistors in series. Opposite to in parallel. In parallel, since you have two choices, we actually sort of increase the flow, increase the current, because we're given options as to which direction we're going to take. We sort of relieve traffic in some sense, but we only have to go through one of the resistors if you imagine your piece of current going through here. And so overall, the net effect is that you have like a weaker equivalent resistance. And so this is the one that you need to add upside down within 1 over R EQ. Now, as for Kirchhoff's laws, so junction law is the law that says that if you have a current, okay, and if you have, as I've drawn this picture here, if you have a current I, and a reminder that I is the variable which we're going to use the symbol A for amps or amperage as the units. The connection between resistance and current is through the voltage, that delta V equals IR, which is the all-important Ohm's law, which you'll come to know and love. V equals IR, or delta V equals IR, is the relationship between these two quantities. Well, if you have a current, which is about the flow of the charges, if we see a junction like this, a point where the current can split, it will split. Some of it will go down and some of it will go to the right. Now, the junction law just says that if you have some I coming in, then whatever comes out, in this case I1 plus I2, must be equal to that incoming I. That's what the junction law says. We can make use of it. We might make use of it in terms of just checking our answer. Or you can make use of it in terms of finding the answer to begin with. The loop law is a little bit more complicated. The loop law says that if you take a pathway, right? So if we start this is about the sort of staircase and the elevator analogy. We start at 0 and the battery lifts us by some voltage amount, let's say 5 volts. If we go through and make any loop, any sort of pathway through this circuit, we can choose any one. We have to end up down at the ground floor by the time that we get to the other end of the battery. So if I went up 5 volts, by the time I go through these resistors, each resistor is going to drop me by some voltage amount. Let's say the first one drops me by 3 volts. The second one necessarily would drop me by 2 volts in order to get back down to 0. Okay, because 3 plus 2 is equal to 5. Um, you can think of it that way, or you can think of it that 0 equals my battery increases me in volts, whereas other elements will decrease me, and 0 has to be equal to those things. You can think of it that way, or just 5 volts equals 3 volts plus 2 volts. It does get more complicated if you want to consider multiple batteries or going backwards in a circuit. But in 107, the problems I'll throw at you, I won't really, I don't like the idea of having, say, multiple batteries in different parts of the circuit, which can make it more complicated. If they're right next to each other, though, if you have another, say, 5-volt battery here, you do have to remember that that would be like going up 10 volts. 5 volts plus 5 volts would go up 10 volts. Much more complicated in parallel, I think. That's the loop law, and it applies even when we split off our pathway. So if I've gone up, I'm just applying the loop law here, if I've gone up 4 volts, went from 0 to 4, if I figure out what my voltage is across that first value, it's going to be the same, or the same idea that, say, if this was 3 volts, then I necessarily would have to go down 1 volt. Now, why it's called the loop law is because I can take any loop I want. If I went this way instead, okay, if I went this way instead, and I already decided that the first one is 3 volts, it actually necessitates that the second one would also be 1 volt. And you'll find that this is true in general, that when things are conducted in parallel, right? If you put your voltmeter here, a voltmeter will have 2 different probes, one that goes at the top and one at the bottom. Say I'm surrounding, and maybe now it's time to change colors here or do some erasing here. Surrounding this bottom resistor here and say that it reads 1 volt. Well, yes, I'm surrounding that resistor, but I'm actually also surrounding this other resistor as well, this other one. It's the same thing. It's actually equivalent to getting your voltmeter and putting the probes over here. It should also say 1 volt. You'll find that in parallel, these voltage differences are going to be the same. Okay, let's get on with the problem and finding what are the currents and voltages across every element in the circuit. Now, when you look at a picture like this, I think, like I said before, you may immediately think of combining the elements. Sometimes we can get away with not doing that. In this case, I don't see of another pathway, another way to do that besides doing this. And why do we want to do this? Why do we want to combine this equivalent circuit if we're asked about each individual element? Okay, well, the reason is because this will get us to, well, in general, if you have volts and you have some resistance, that's going to get you to a voltage in some way through V equals IR. And if I was to combine everything and put them into this equivalent format here, then what I'm able to find is, since I have this voltage and this equivalent resistance, I would be able to find the current I that goes through this imaginary resistor. But that current, due to the junction law, since there's no junctions, and let me go ahead and call it IEQ, I guess. Since there's no junction, that current would actually be the same current as the current that goes through the battery. And that's actually part of the question here, is we need the currents and voltages across the battery as well as the resistors. And so that would be IB. Okay, and once we have that, it's going to help us find the other parts. So yeah, the step one here is going to be finding the equivalent circuit and equivalent uh, and in order to get to that current value. This is already a challenge, right? If you recall from the capacitor problem, you've got to decide which two elements to add together. And if you followed along with that one, you'll see that this is not a good choice. We cannot combine R1 with either of these values because the junction really, really messes things up. But what we can do is we can combine these two, the ones that are in parallel, and let me surround that junction as well. These two, and sort of break them down into the first step being just combining the 2 on the right, the 2 and the 3, and forming this R23 equivalent resistor. Okay, so R23, since these are in parallel, this is going to be opposite to the capacitors. In parallel, we get the nice equation. In parallel for resistors, we get the mean equation. So this is going to be 1 over 2 ohms plus 1 over 3 ohms. Okay, and again, for here, you can, we'll do the fractions this time. Rather than use our calculator, we can find a common denominator. 1/2 is equivalent to, well, least common denominator here is going to be 6. So 1/2 is equal to 3/6, and then ohms on the bottom, and 1/3 is equal to 2/6 ohms. Put those together, that's 5/6. Okay, 1 over R23 equals 5 over 6 ohms. And so we can cross multiply. Let's practice doing that this time. That means 1 times 6 ohms is equal to 5 times R23. Divide by 5, and so R23 is equal to 6/5 of an ohm. Notice 6/5 is equal to, well, 6 divided by 5 is equal to 1.2 ohms. Notice that this value is smaller than both 2 or 3, and this is going to happen very often with parallel resistances or parallel or series capacitances. It's going to be smaller than either of its parts. Having one equivalent resistor is going to be weaker. Like having these two in parallel, a 2 ohm and a 3 ohm next to each other, actually creates a lower resistance somehow. Very interesting phenomenon. So let's clear some of our board here. Well, how about we make our new circuit first. So this here is that 1 ohm resistor, this R1. We want to, now we're at the step where we want to combine these two to form R123. We're going to want to form this circuit, and with this newfound information that actually R23 is equal to 1.2 ohms. And then let's go ahead and erase all this and try to move on with this R123. Now, because if we look at the picture, the blue picture on the bottom left, because these guys are in series, now we get the nice equation. We only need to add them directly. Okay, and so R123 is equal to that 1 ohm plus, right, so this 1 ohm right here, plus R123. I'm sorry, R23, which is 1.2 ohms. And so our equivalent R123 is equal to 2.2 ohms. Nice. So now we have broken the circuit down into just one piece. How do I get the voltage, or sorry, not the voltage, the current, which was what the whole point of doing this for was? Well, if I ever know my resistance and my voltage, then I know I can find my current, because since V equals IR, that means I equals delta V over R. And in this case, that's 4 volts divided by 2.2 ohms. And so 4 divided by 2.2, 1.818 amps. We're partway to the answer, right? I mean, I'm asking about every little piece, the voltages and the currents. But if we are talking about the battery, well, the current is equal to 1.818 amps. And the voltage is actually given. Delta V is the 4 volts. No math there. That's given. Now, the rest of it, we have to use Loop's law and the junction law in order to make some inferences. In fact, the junction law is going to help us right away, very quickly. And here is why. We have figured out that the current across this this battery, this first element, is 1.81. Let's look at our original circuit. Let me erase some of these markings to give us some space to look at this circuit and transfer over this 1.81, let me call it IB, current. Notice there's no junction between IB and the first resistor. What does that mean? Well, the current only changes after it sees a junction. And so since the current is going across this first battery here is 1.81, it's not going to change by the time that it reaches I1. The first resistor is going to have the same current. I1 is also equal to 1.81. There was no junction. We need a junction if we want to change the current. The junctions change current, and we didn't find anything. Okay, this is going to be like a puzzle piece. Once you sort of lay one down, you can find the next missing piece. You'll see the holes sort of start to emerge, and your puzzle piece is ready to be locked in, because I don't know my voltage across the first element here, but what I do know is I know the current across that resistor 1, but I also know the resistance across resistor 1, and so that brings us back now to Ohm's law. I just need 2 of these 3 things in order to find the third. So since I know the current and the resistance, I can also find delta V1 is going to be equal to I1, which is that 1.8, and it looks like my period is not really sticking. Draw it again. 1.818 amps. V equals I, and R is that 1 ohm. So my delta V1 is equal to 1.81 volts. 818 volts. Nice. Very nice. We've got our R1, and now we can keep going. If I wanted to try again and say, look, oh, my current is 1.8, can I just keep it going? Not anymore, because now I've got a junction. It splits. It's not obvious what the currents are on these sides. But now we can switch gears, and now we can go over to the loop law, R2, right? R2. We don't know what I2 is, but we're going to be able to find delta V2 to the loop law, okay? Now, how is that? How are we going to find delta V2? Erase these markings again. Now, the loop law says that if we go up by 4 volts, by the time we come back down, we better get back down to 0. If only we knew how many volts were across here, right? If this was 2 volts, then there would be 2 volts left for R2. We just figured it out, actually. This is 1.818 volts. And so, if I get that, so 0 equals 4 volts minus 1.818 volts minus whatever the voltage is across that second element, that's going to be one equation we can use. In other words, if I just sort of add delta V2 to both sides, then this is like saying, sorry, not minus, not plus, or minus and then plus, we get 0. Add it to both sides. 4 minus 1.818, and I get 2.18. Delta V2 now is equal to 2.18 volts. 2.18 volts. And that now slots in the next piece of the puzzle because I have delta V2 and I also have R2. R2 is 2. So how do I find I2? Well, since V equals IR, I equals V over R. So I2 is equal to delta V2 over R2, which is 2.18 volts over 2, or 1.09, over 2 ohms, 1.09 amps. 1.09 amps. It's very messy. I'm trying to keep it all on one page, but surely you in your nice, clear homework submission will just put this on a separate page and give me a whole 1 or 2 pages that it takes to actually do this problem out. R3. Now we're down to R3, and we can use either law to get us an answer because we have quite a bit of information now, actually. Since we just did the loop law, let's jump back into Kirchhoff's law. We can use that idea that the voltages will be the same. Since they're in parallel, R2 and R3, the voltages would be the same. But we can double check that idea with the junction law, right? So this is IB, it's that 1.82 amps, or 1.818. This is still 1.818. Here it has split, it's gone down and then to the right. So this part is 1.818 amps is the current. Well, this one over here, let's do it in a different color. This one we decided was 1.09 amps. Then the one on the right must be the rest. It must be 1.818 minus 1.09. So 0.72. 0.728 amps. Because now this green and this blue will add up to the purple. My current in equals the sum of my current out. It'll be the opposite when we get over here. My green plus my blue will equal purple, but the same exact equation. And so I3 is equal to 0.728 amps. I could have managed my colors a little bit better. I'll try that next time. But hopefully you are seeing what's going on here. And now we're missing just one thing, which is delta V3. But once again, we learned a new piece of information. We learned that I3 is equal to that 0.7 amps. And so we could use uh, Ohm's law one more time, that that voltage is going to be the current 0.728 times the resistance, which is 3, or 2.184. 2.18 volts. This is my answer. And actually, let's double check with that idea that we said before, that since this uh, middle resistor and this outside resistor, they're connected in parallel, they should have the same voltage. And indeed they do. They're both 2.18 volts. If you get anything just a little bit after that, it's just rounding issues. Nothing to worry about in this class. But those are the same due to Kirchhoff's loop law, that if you take either pathway, we're going to raise by 4 volts, drop by 1.8 volts after the first one, and then the rest of the drop has to happen in either pathway, whether we go around this way through R2 or this way through R3. We have to have the same voltage drop so that we can get to the ground floor of 2.18 volts. All right, hopefully those junction law and loop law make a little bit more sense. They can be very confusing, especially Kirchhoff's loop law. If the combination or adding together these resistor components, if that part was confusing, I would say rewatch the capacitor problem. But if Junction's law or the loop law just sort of still don't make sense, they're still a bit mysterious, you want to double check, please write your questions down and bring them to me. These are some good equations, good ideas to understand. They're not very, I think, intuitive, but you can sort of play with it, and then it sort of makes more sense. We're going to do some labs which look a lot like this, and you can compute the voltages and the currents, um, and we're going to build them in real life. Okay, so bring me any questions. Thank you, folks.